Our next one is looking at the most stable conformation. It says for cis 1-methyl 2-isopropyl cyclohexane. Make certain that you're looking at the correct structure. It is indeed the cis. Now we know we like the substituents in the equatorial if at all possible, but don't just jump and say, ooh, both of them are equatorial right here. That's the correct one. We got to first see if they're cis or trans. So you need to know where these are located. Here's the hydrogen. Methyl's axial, hydrogen is equatorial. It would point out. This one would point out. So if you take a look, here the isopropyl is on the bottom, methyl is on the top. This one is trans. That's not the right compound. The question asks for the most stable conformation of cis. This one's the trans. You look at this one. There's where the hydrogens would be. So we've got isopropyl on the bottom, methyl on the bottom. They're both on the bottom. This is indeed a cis. So that's the correct structure. Looking at the next one, here's where the protons would be. So look at what is top and bottom. Methyl's on the bottom, hydrogen on top, methyl on the bottom. Here isopropyl's on top. So you got bottom, top, that's opposite sides. This is trans. That's the wrong molecule. And finally we have methyl on top, isopropyl on top. They're both on top. That is a cis isomer. So we've got two of them ruled out already. The two that are trans. That's not what the question asked for. The question asked for the cis one. Looking at the two cis, one of them has the methyl in the equatorial, isopropyl in the axial. And the other one has the methyl in the axial and the isopropyl in the equatorial. So we said it's more stable to have the larger group in the equatorial if you have to make a choice. We'd like to have both of them equatorial, but we can't with the cis isomer here. So it's more stable to have that larger isopropyl group in the equatorial. So D there is the most stable conformation for that molecule. Let's take a look at some nomenclature. First one here on nomenclature, we have a bicyclo compound. I'm going to highlight the two bridgehead carbons. I'll highlight those in red. Those are our bridgehead carbons. Let's just go ahead and get the total number of carbons in each bridge, so we're going to need that in our name. So going around here to the left, I have a carbon here, carbon here, carbon here, and here. So there's 4 carbons in this bridge. If we go over the top, from bridgehead to bridgehead, there's 1 carbon in that bridge. If you go around to the right here, I have a carbon and a carbon, going from bridgehead to bridgehead. So we have 2 two carbons in that bridge. So this is a bicyclo, brackets, and this is the number of carbons in each bridge. It's a 4, a 2, and a 1. You start with the biggest and go to the smallest. It's a 4, 2, 1. And then all total, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 carbons all total in the rings. So this is a no name. It's a bicyclo 421 no name. Now we still have a methyl to take care of. There is a methyl group hanging off out here, and I need to know where it is. So let's number the ring. Now if you recall the rule, we must start with a bridgehead carbon. We're going to start with one of these two bridgehead carbons. You must also go into the larger bridges first. So I'm going to start here. Here's number 1. And we must go into the 4 carbon bridge first. 2, 3, 4, 5, and then we're back to the other bridgehead. Now I've got to decide, do I go to the 2 carbon or the 1 carbon? We go to the 2 carbon. We go to the biggest bridge first. So we went to the 4 carbon. Now we have to do that same decision again. We go into the 2 carbon bridge. This is 7, 8. And then finally we go into the 1 carbon bridge. There is 9. Now if you had numbered, if you'd started with the other bridgehead carbon and number around, you'll have the methyl group on number 8. You can try that if you want to. It's smaller on the 7. So this is a 7 methyl bicyclo 421 no name. We're finished with it. Looking at our next one. Again, I'm going to highlight the 2 bridgeheads. This is also a bicyclo compound. There are the 2 bridgehead carbons. So this again is going to be a bicyclo. We got brackets. And in the brackets is the number of carbons in each bridge. So let's take a look at that. If we go around here to the right, from bridgehead to bridgehead, if you go around the right, you come across a carbon, carbon, carbon. You got 3 carbons in that bridge. That's our biggest bridge. If you go around to the left, carbon, carbon, and then we're back to the other bridgehead. So you got two around this way. And if you go straight across, bridgehead to bridgehead, there are no carbons in this bridge. Would be a 0. This is the bicyclo 320. Now all total, we have 7 carbons in the rings. So as an alkane, that would be a heptane. But it's not an alkane, it's an alkene. We got a double bond. What do we do now? Well, just like you do any of the alkenes, drop the A and E off of the alkane name and add E and E. Now we need to tell the position of that alkene, and we also need to know the position of our substituent. So we're going to number the ring. We have to start with the bridgehead carbon. And you must go into the bigger bridge first. And then we'll go into the 2 carbon bridge. And we're finished. Now, I numbered it correctly here. If you had started with the other bridgehead carbon and make that number 1 and number on around, got to go into the bigger bridge first, and then into the 2 carbon bridge, you would have had the substituent on carbon number 7. It's smaller to have it on carbon number 6. Now the double bond is going to begin on number 6 no matter which way you go. We want as small a number as possible for the double bond. It takes precedence over the substituent, but it's carbon number 6. It starts on carbon number 6 no matter which way you number. You can start with either bridgehead and you'll still get number 6 both ways for the double bond. But only this way will give a 6 for the substituent. The other way will give a 7 for the substituent. Now we do need to tell the position of that double bond. The double bond starts on carbon number 6. So I'm going to put the 6 right in front of the ene. You could put the 6 here in front of the bicyclo 3210 heptene, but that's just so far away it's very confusing about what that 6 goes to. I just think it looks better to have it right in front of the ene. Now we have the substituent to take care of. We have an ethyl group on carbon number 6. Substituents go out in the very front of everything. So this is a 6-ethyl bicyclo 320 hept 6-ene. Looking here at the next one. Now this is not a bicyclo. Even though we have 2 rings, it's not a bicyclo compound. Bicyclos must share 2 carbons. And all the rings will share 2 carbons. I have 2 rings, but they don't share any carbons. They're just 2 rings connected to one another. They're not sharing any carbons. So there are no bridgehead carbons. So, got 2 rings. You're going to go with the bigger ring. It's got the alcohol on it, but alcohol takes precedence over everything. So the big ring as an alkane. There's 6 carbons in the ring. It'll be a cyclohexane, but it's not an alkane. It's an alkene. It's got a double bond. So we change our ending from A and E to E and E. So it's a cyclohexene. Well, not only is it a cyclohexene, it's an alcohol. So for alcohols, you drop the final E and add OL. So this is a cyclohexenol. Now we need to number that ring so we know where everything is at. The alcohol takes precedence in numbering. So the carbon there with the alcohol is going to be the number 1. Now we got to figure out, do we go clockwise or counterclockwise? The alkene takes precedence over the substituent in numbering. So we want as smallest number possible for that alkene as we can get. So this would be 2, 3, 4, 5, and 6. So the double bond begins on carbon number 3. Now I need to indicate that in my name. You can put the 3 here in front, or you can put the 3 there directly in front of the ene. I like it in front of the ene better, so that's what I'm going to do. That's just a personal preference. You don't have to tell the position of the alcohol here in the ring, because in the ring there is no end like there is in a chain. So we can start numbering anywhere, and we always start with the alcohol because it takes precedence in numbering over everything else. So in a ring, the alcohol is always on carbon number 1. So I don't have to tell that. If you want to, it doesn't hurt anything. You can put a 1 there in front of the all. Doesn't hurt anything. Okay, so last thing we have left is the substituent. On the number 5 carbon, we have this ring. That's a cyclopropane ring, but as a substituent, all of our substituents end in YL. We change our ending from the A and E to a YL. So that's a cyclopropyl group. And it's on the number 5 carbon. 5-cyclopropyl, again, notice that ends in YL. Substituents always end in YL, like methyl and ethyl and propyl. So it's a 5-cyclopropyl, cyclohex-3-ene all. Next one, we have another ring here. That ring is 5 carbons in the ring, so that is a cyclopentane. And we don't have any alkenes or alcohols or anything, so we're finished with that part. That's our parent, cyclopentane. We have some substituents hanging off. Up here we have a methyl group. Here, there is 2 carbons in that chain. That is an ethyl group. And then off of that ethyl is a bromo. So on carbon number 1 of the ethyl, we start number 4 connected to the ring there. Off of carbon number 1 is a bromo group. And we're going to put all that in parentheses so we know it's all one group. So it's a 1-bromo-ethyl group. Now, we need to put those substituents out in the front and tell their position on the ring. If I start numbering with the methyl carbon on the ring where the methyl's attached, that one number 2, 1, we got 2, 3, 4, 5. I have the methyl on carbon number 1 and this 1-bromomethyl group on carbon number 3. If I start numbering where the 1-bromoethyl group is, make that number 1, then the methyl's on carbon number 3. Well, it's a tie. It's a 1-3 versus a 1-3. What do we do when there's a tie in numbering? We give the lower number to the one that comes first alphabetically. So the 1-bromoethyl is going to get the lower number over the methyl. So the green one there that I've got, green is the correct one. The blue one was wrong, so I'm going to take the blue one off. Okay, so substituents go out in front in alphabetical order. So this is a 1-bromoethyl. And then a 3-methyl cyclopentane. And we're finished with that one. So our next one here is looking for the most stable conformation of 1,2-dichloroethane. Now, first thing that we need to do is make certain that they're 1,2-dichloroethanes. let's just examine these structures first before we start trying to pick out most stable or least stable. Make certain they are 1,2 dichloroethanes. So remember, this is our front carbon, the circle is the back carbon. So if you look at this one, our front carbon has got a chlorine on it and another chlorine. This is a 1,1 dichloro, not a 1,2. Both chlorines are on the same carbon. They're both on the front carbon here of our Newman projection. So this one is out because it's just the wrong compound. This is a 1,1 dichloro. Now if you look at the others here, here's the front carbon, circle's the back carbon. This has got a chlorine on the front carbon and a chlorine on the back carbon. That's a 1,2 dichloro. This one's got a chlorine on the front and there's one on the circle. That's a 1,2 dichloro. We're good. This one has a chlorine on the front carbon and a chlorine on the back carbon. We're good. That's a 1,2. This one is the same thing. Chlorine on the front, chlorine on the back carbon, 1,2. That's good. Okay, so it's between those four. First one's just the wrong compound. Now it asks for the most stable conformation. The most stable is to get those substituents as far away from each other as possible. That's to have the chlorines on opposite sides. This is the anti-conformation. They are anti to one another. They are as far away from each other as they can possibly get. That's the most stable. It's in circle, the most stable. So there's the most stable. Second part of the question said place a square around the least stable. Well, the least stable is an eclipsed conformation. This one's eclipsed and that one's eclipsed. So it's one of those two. Here we have the big, large chlorines eclipsed. They're on top of each other here. Here is a chlorine on top of a little bitty hydrogen. Chlorine and a hydrogen on top of each other. So that's bad, but not as bad as having two big chlorines on top of each other. This is the least stable. That's the worst one. That's the highest energy one. Anti is the most stable, the lowest energy one. Our next question, we have some more naming. Now the first one that we have here has an alcohol group. If you recall our rules for the alcohol, you must include the carbon bearing the OH group in your longest chain. You must find the longest chain that has that carbon in it. The longest chain that has that carbon is this one here. That's our parent chain. Let's number our chain. So that one had 7 carbons. I do have 8 carbons straight across, but I can't use that because you must include that carbon that has the OH in your parent chain. Let's number our chain. We start with the end the OH is the closest to. It takes precedence over the substituents. We have 7 carbons there in the chain. As an alkane, that is a heptane. The alcohol, for the alcohol, we drop the E off the end and add OL. So this is a heptanol. I must tell the position of the alcohol group. It is on carbon number 2. You can put the 2 here in front of the parent name, or you can put the 2 in front of the all. Personally, I like the bottom one there better, but either one is perfectly acceptable. Now we have a couple of substituents to take care of. We have a methyl, let's just write them out here. Got a methyl on carbon number 4. And on carbon number 3, we have a propyl. There's 3 carbons in that substituent. So we have a propyl. Those go out in the front in alphabetical order. So methyl comes first alphabetically. 4 methyl, 3 propyl, 2 heptanol, or it's going to be 4 methyl 3 propyl heptane 2-ol, whichever you prefer there. Looking at our next one, this one's got a lot in it. We've got a couple alcohol groups, got an alkene. Alcohol, rules for the alcohol said we must include the carbon bearing the OH group. You must include the carbon bearing both of them, and it happened to be on the same one, but if they were on different ones, you would have to include both of those carbons in your parent chain. When we did alkenes, we said we must include both carbons of the double bond in our parent chain. So we have to include all 3 of those carbons in the parent chain. Find the longest chain that contains all 3 of those carbons. And just so happens it's all of the carbons. They're all in the parent chain. There's our longest chain. It contains all of them. Let's number the chain. We start with the N that the OH, the alcohols are the closest to. They take precedence over the double bond in numbering. We have 6 carbons in the chain. 6 carbons as an alkane would be a hexane, but it's not an alkane, it's an alkene. So we drop the A and E and add E and E to represent the alkene. So this is a hexene. Not only is it an alkene, it's an alcohol. Now with one alcohol, we always drop the final E and add OL. There's 2 of them. 2 alcohols would be a diol. You got 3 alcohols as a triol. So the diol, since it starts with a consonant, we're not going to drop the E, because if you drop the E and put diol, it gets hard to pronounce. You got the 2 consonants together, and it's difficult to pronounce. So we leave the E when our suffix starts with a consonant. We drop the E if it starts with a vowel. So we're going to leave that E on there and do diol. It's a hexene diol. Now, I need to tell the position of everything. The alkene starts on carbon number 4. Now you can put the 4 in the front, or you can put the 4 in front of the E. The alcohols, both of them, are on carbon number 2. That will have to go right in front of the diol. You must tell the position of both of them, not just one. You got to put the 2 twice, because you got to tell where both of them are. So it's a 2,2 diol. Now we've taken care of everything in the chain, and we've taken care of our functional groups. Should be done. Watch out on these alkenes. If you can tell cis and trans on them, if that's shown, you've got to indicate that out in front. So this one, if we got so much on there, let me erase some of this off here. So much stuff there, it's hard to see. There's our double bond, or alkene. And this is a trans double bond. See, there would be a hydrogen this direction and a hydrogen this direction. So you got substituent, substituent. They're on opposite sides of the double bond. And the hydrogens are on opposite sides of the double bond. That's a trans alkene. So that just goes out in the very front. This is a trans 4 hexene 2,2 diol, or you can put that 4 in front of the ene, whichever way you prefer. Now we're finished. Our next one here, we need to find our longest continuous carbon chain. Let's see, if we go straight across, got 6 carbons. However, if we go this way, we also have 6 carbons. Okay, we have a tie. Excuse me. A tie in choosing the parent. When we have a tie, we go with the one that has the chain that has the most substituents. If you follow the red one along, coming along on the red one, mark this down. Following along the red one, got a substituent here hanging down, following along, got a methyl hanging down, got 2 substituents with the red one. If you look at the green one, let me just take the red off here. It's wrong, by the way. The green one has 3 substituents. Look at the green one, it's got a bromo hanging off, it's got an ethyl hanging off, and you got the methyl hanging off. The green one is the correct one. Now we want to number it to give the substituents as low a numbers as possible. And that will, you can try it both ways, but starting on this end will give you the smallest numbers. Okay, so our parent is a hex with 6 carbons, it's a hexane. And we have, let's just write it, we have a bromo on carbon number 2. We have an ethyl on carbon number 3, and a methyl on carbon number 5. So our substituents go out in front in alphabetical order, so bromo comes first alphabetically. So this is a 2 bromo, 3 ethyl, 5 methyl, hexane. 2 bromo, 3 ethyl, 5 methyl hexane. Our last one here on the old exam this one has got 2 alkenes in it, so our rule there for alkenes, we must include both carbons of the double bond. So with this one here, I must include both of those carbons in my parent chain. Well, with this double bond, I must also include both of those carbons in my parent chain. So I must find the longest carbon chain that contains all 4 of those carbons. That one there. We're going to number our chain to give the double bonds as low a number as possible. Remember, the double bonds take precedence over our substituents. Eight carbons as an alkane would be an octane. It's not an octane. It's an alkene. Now normally we drop the A and E and add E and E, but there's 2 alkenes, so it's not an ene, it's a diene. Diene starts with a consonant, so that's going to mess things up. Normally we drop the A and E, and if I put diene, then that gets difficult to pronounce. We've got 2 consonants together. So what IUPAC does is leave the A, we just drop the N and the E, and leave that A, and then put the diene. It's an octadiene. We need to tell the position of the two double bonds. One of them starts on carbon number 1, the other one begins on carbon number 5. This is a 1,5 octadiene, or you can put the 1 and the 5 in front of the diene. Now we have some substituents to take care of. We've got some methyl groups. We've got 3 of them. 2 of them are on carbon number 4. You got 1 on carbon number 7. So 3 methyls. That will be a trimethyl, but you must tell the position of all of them. So this is a 4, 4, 7. There's my 3 numbers there for the 3 substituents. Trimethyl, 1,5 octadiene, or you can put the 1,5 in front of the diene. So 4, 4, 7 trimethyl octa 1,5 diene. Okay, that finishes our old exam. Now, in going through this old exam that I just covered here, I noticed there is not an IHD question on here. There will be an IHD question on your exam. So, index of hydrogen deficiency. Be able to calculate the IHD if I give you a molecular formula. I don't know why there wasn't one on this old test, but there wasn't. Maybe we had a different edition of the textbook at that point. I know they moved that section around. But make certain you can do an IHD, index of hydrogen deficiency. So I went through that very carefully this morning in lecture. So look back through your notes. I promise you there will be one of those on there. I think everything else is pretty well covered. So you got a lot of acid-base reactions, and then some being able to put things in order of basicity or acidity, and then a lot of naming. Conformational analysis as well, and then our IHD.